Hi there, in this handout we're going to look at two special polynomials. The first special polynomial is one that we can model using algebra tiles, and I've drawn up a set of algebra tiles here. And the first thing I'm asking you to do is to look at these algebra tiles and see if you can figure out the binomial factors. So we can do that just by drawing in our tiles here. And what's the top row? The top row would be an x plus a 2. The left column is also an x plus a 2. And I guess that's all equal to whatever's inside here, so that's x squared plus 1, 2, 3, 4x plus 4. Alright, what do I notice about this? Well, I notice the binomials are the same. The factors are the same. It's like x plus 2 squared. There's two of them. Just like when you figure out the area of a square. And then I'm asked, can I draw another set of algebra tiles with the same pattern? And for sure I can. I think I just have to draw something that's square. So try this. Keep everything square. That looks like a square to me. Let's factor out the binomials and see what I get. So there's an x, and a 1. That's an x, and a 1. So this is a 2x plus 1 on the top and on the left row. Yep. I'd say that is 2x plus 1 squared. And I'd also be able to count this 1, 2, 3, 4x squared. 1, 2, 3, 4x plus 1. Alright. Well, let's see what this where this takes us. So what we're actually looking here at are perfect square trinomials, and they're trinomials that have this particular form. And there's a squared plus 2ab plus b squared is equal to a plus b times a plus b. And for sure I see this pattern here. That's like saying a plus b, a plus b. So this is where a is equal to 2x, b is equal to 1. Which I guess that means if I wanted to look at a squared, that would be 2 squared plus x, so that's 4x squared, and b is equal to 1. Now, let's see how this works. 4x squared is the same as a squared, so I can say that's a squared. 4x is the same as a times b times 2, so that's 2ab. And 1, that's a b squared. So I think through this example we can sort of see that this relationship holds true for these special square trinomials. Let's take a look at this example here and see what it tells us. Let's check to see if it's a perfect square trinomial. So the first question is 4a squared a perfect square? So in other words, if a squared is 4a squared, can we find out what a is? And yeah, that's like 2y. So that is a perfect square. 25 is most definitely a perfect square. So if b squared is 25, b is 5. So that's like the idea of a plus 2ab plus b squared. Sorry, a squared. So 2ab, so we got 2, a is 2y, b is 5, that's equal to 20y. So I'd say yeah, this meets all the things we're looking for special perfect square polynomials. Let's look at trying to expand some of these. So here I have a 7 minus c all squared. So if I look at this relationship here, I could say that's an a and the c is a b. So these two kind of match. So I know if I expand I should be equal to this. So a squared is 49 minus 2ab is 2 times 7 times b. So that's 14b sorry, 14c. And b squared is c squared, so it's plus c squared. But we can check this by doing our normal, or the expanding stuff we did previously. So 7 minus c minus 7 minus c. So we got 49 minus 7c minus 7c plus c squared. So yeah, we can see those. We can expand and simplify either way. The next one we're asked to look at is this guy. Let's check and see if it's a perfect square. So that's a squared minus 2ab plus b squared. A would have to be 4x. Oops. B would have to be 2y. That's supposed to be a square. And 2ab would have to be 2 times 4x times 2y, which would be 16xy. So I'd say that works out. Oops. So this is equal to an a minus b all squared. That's equal to 4x minus 2y squared. And we can't factor this anymore. We can't take out a 2 because remember we're squaring both these things. So that's the factored form. Okay, the second special trinomial we're looking at is called the difference of squares, and it too can be modeled using pictures and diagrams. So I've drawn a sort of shape here. It's a square with a chunk missing, and I've kind of dimensioned or given sizes. So the square has like a side length of a. So if we were to take the total area of this that's colored, so the checkered, the dark, and the gray, we end up with the area of a squared, so a times a, this is here, minus this little corner here, which is b times b. So the total amount of colored stuff is a squared minus b squared. We can also think of it in terms of something else. We can say, well, if we take this area here, we get a times a minus b. So that's this a times a minus b. And then the light colored area, this, so that's b times a minus b. So that's this. So if we total up the colors that way, we get this. And we can factor that out by saying that's a minus b plus b a minus b. So that's the same as saying a plus b times a minus b. And that has to be equal to the same thing up here. So that's the property of the difference of squares. So factoring with the difference of squares. It's not too hard actually. We just have to identify if something's a difference of squares. So when we go to factor this, if we can identify that if this is true, then we can factor it very easily. So if you can take the square root of 36, so that means a is equal to 6. The square root of negative b squared would be 2b. So the factor of this would be, so if you think a plus b, a minus b, so that's 6 plus 2b, 6 minus 2b. We can try factoring this one as well. If we say a squared is 49y to the fourth, therefore a equals 7y squared. And if b squared is 100x squared, b must be equal to 10x. So if we factor that, we get 7y squared plus 10x, 7y squared minus 10x. So it's a powerful way to factor some convenient difference of square trinomials. So once you're feeling okay with this stuff, try these questions. I think 20 might be a bit challenging, but the rest hopefully you can do without too much trouble. Alright, good luck.